Hey, this is Mr. Janes. In this video, we're going to be talking about transformations and symmetry in one figure. Specifically, we're going to talk about transformations that, when they're performed, map a shape or a figure onto itself. So that means we're looking for things like reflections and rotations that once we do them, it doesn't change how the figure looks. So, reflectional symmetry. Reflectional symmetry is if you have a line of reflection in a shape, a figure, a picture, that when the shape is reflected over that line of symmetry, it still looks like the original shape, maps to itself. So for example, this shape right here, this do not enter sign, when it's reflected across this line of symmetry, it's going to look like the same exact figure. You can tell because every part of this figure on both sides of the line of symmetry is the same distance from the line of symmetry. This H right here has two lines of symmetry. One that is vertical, notice how everything on both sides of that line of symmetry is the same, and one that is horizontal, notice how everything on both sides of that line of symmetry is the same. Some people are tempted to say that there is a third line of symmetry right here. Now we know that it's definitely not a line of symmetry, because if you look on both sides, for example this side, you can see the top of the H right here, but the other side, there's no top of the H right there. Similarly, right here, the H is extending out in this direction, and for it to be symmetrical, the H would have to be extending out in this direction. But that does not happen, and so the H only has those two lines of symmetry that I showed you before, and not the diagonal. We can also have rotational symmetry. Rotational symmetry means that we would rotate the object, just like this, and after a certain number of degrees of rotation, we would get back to the original object. Both of these images here have rotational symmetry. The first one, well, let's kind of break this into three right here. If I were to rotate this object that much, it would be the same image. We can show that right here if we do that. So if I take this and rotate it, and right about there, we get back to the original image. And we can do it again, and one more time. So it has rotational symmetry. How much? Well, this arrow right here is showing us a 1/3 rotation. And if a circle has a total of 360 degrees, then 1/3 of that is going to be 120 degrees. So this has 120 degree rotational symmetry. What about these birds? The birds have what we would call 90-degree rotational symmetry. If we were to take the birds and rotate them only 90 degrees, we would get back to the original image, just like that. So this is going to have 90-degree rotational symmetry. Okay. You might be tempted to say that the birds also have reflectional symmetry on this line, but in fact they do not. If they had reflectional symmetry, take a look at this. The head of that bird is right there. If that was reflected over, then the head of that bird would have to be right here, and the tail would have to be right here. But in fact, that's not the case. The head of the bird is down here. So there's no reflectional symmetry there, only 90-degree rotational symmetry. What I'd like you to do now is pause the video and try for these next 8 figures to draw all the lines of reflectional symmetry and name the angle of any rotational symmetry. Note, some figures may have infinite lines of symmetry. Pause the video now, try and fill those in. The answers to the first 4, or the top row, will appear in 3, 2, 1, and here they are. The first one has 2 lines of symmetry, of reflectional symmetry, there and right here, and has 180-degree rotational symmetry. Some people might say it has 90-degree rotational symmetry, but it in fact does not have 90-degree rotational symmetry. Watch what would happen. If I turned only 90 degrees, it does not look like the original shape. If I turn a full 180 degrees, it does look like the original shape. So, 180-degree rotational symmetry. The second shape, the isosceles triangle, has reflectional symmetry, but not rotational. Notice if I try and spin it any way, okay, I cannot get it to look like the original figure unless I go, I guess, 360 degrees, which would just be like not moving it at all. This right here, no reflectional and no rotational. The last one, no reflectional, but it does have 120-degree rotational symmetry. I'm going to reveal the last 4 in a second. They're coming up in 3, 2, make sure you've tried them, and here they are. And here we are. The x has 8 lines of symmetry, or I should say 4. 1, 2, 3, 4. And it has 90-degree rotational symmetry. Again, if we took that x and rotated it 90 degrees, boom, we would get the same figure. This hexagon has, looks like 6 lines of symmetry. 1, 2, 3, 4, 5, 6. 6 lines of reflexive symmetry. And 60-degree rotational symmetry. Again, if we move that only 60 degrees, we get the same hexagon. And to figure out 60 degrees, remember, we just take the full 360, and notice that we only need a sixth of a turn. So 360 divided by 6. Again, 6 sides, 1/6 of a turn, 60-degree rotational symmetry. Over here, we've got a star that has 5 different sides, so it ends up having 5 lines of reflexive symmetry, and 360 divided by 5, or 72 degrees of rotational symmetry. As for the circle, well, the circle, think about this for a second. Where can I draw a line through the circle so that it's reflecting on itself? Well, actually, you can do it anywhere. Anywhere. So it's got infinite lines of reflexive symmetry. And what about rotation? Well, we could rotate it, I guess, any amount and have it look the same as it did before. And just to show you, here's my circle, and I can rotate it any amount, right? It does not change the circle in any way. So it has infinite lines of rotational and reflexive symmetry. What I'd like you to do now is pause the video and try and do questions 1, 2, 3, 4, and 5 on your own. Then unpause the video when you think you have some good answers, or maybe you're a little confused and you need to check out what the answers are. I'm going to go through and do these all out in just a few seconds, so make sure you pause the video now. And the answers will be coming in 3, 2, 1. All right, let's take a look at number 1. A triangle has an angle of rotational symmetry of 120 degrees. What kind of triangle is it? Well, let's think about this for a second. We have a triangle, any triangle right here, and it has rotational symmetry of 120 degrees. That means that I could take this triangle, okay, and turn it 120 degrees, and it would be the same triangle. So imagine again, if I took this triangle and rotated 120 degrees, that would be the same triangle. Now, I didn't draw it very well here, but you can imagine what kind of triangle would do that. Well, whatever triangle did that, it would have to have the same angles here as it did, let's rotate, as it did on all of the corners, I guess, because they've all got to be the same. And I guess they'd all have to have the same sides too, because they've got to rotate onto each other, which means it's going to have to be an equilateral triangle. Okay, so this is going to have to be an equilateral triangle. So use what I just said and write down yourself a little explanation of why it's got to be an equilateral triangle. Okay, I'm not going to write this down for you. You do yourself. Number 2, 3, and 4 over here. A regular pentagon ABCDE has exactly 1 line of symmetry as shown. There it is right there. What is the image of point C under a reflection? So if I take C and reflect it, what does that become? Well, right across, it's point D. Are there any fixed points under a reflection? Any points? Remember, fixed points are points that do not move. Well, A is on the line of symmetry, and so if we reflected this shape over that line, A would not move, would stay right there. So A is a fixed point. Which sides of the pentagon must be congruent? Well, let's think. If this pentagon maps to itself, it reflects into the same shape, that must mean that this side is congruent to this side, and that this side is congruent to this side. Because if that's the line of symmetry, then those have to be the same. So I would say that ED, line ED, is congruent to segment BC. I'm sorry, these are both segments. And that segment EA, okay, is congruent to segment AB. Okay, and that's all because the segments on both sides have to be congruent because they are a reflection of each other. Now, if you didn't quite get question 5, make sure you pause here before I show you some answers to 5. All it's asking you to do is draw a figure that meets each of the properties in the space to the right. So, try to make a figure for each of these things right here. Now, the answers are about to pop up on the screen, but when I show you these answers, do not copy them down. Draw your own figures. There's an infinite number of possibilities for each one of these questions. right? So don't just copy down what I have. Take a look at what I have if you're confused and try and draw your own. So, first, A, an angle of rotational symmetry of 90 degrees. Well, the easiest thing to draw would be a square. Okay, because if I took a square, right, and I move that 90 degrees, then it's still going to be a square. You could have also drawn the x that we saw before, right? Because if I take that x and rotate it 90 degrees, right, I'm going to have the same x. One that I like to draw is kind of a pinwheel, right, like this, if I can do this well. Takes a lot of artistic skill here. This also has an angle of rotational symmetry of 90 degrees. Move 90 degrees and you've got the same pinwheel. For B, an angle of rotational symmetry of 72 degrees. Well, this might stump you a little bit. But remember before, we had this shape right here that had a 72 degree rotational symmetry. Why did it have that? Well, remember because it 1/5 of a turn and it was back to the same star. So we need to create another shape that somehow has maybe 5 sides or five rotational something or other. How can we do that? Well, the easiest way to do it is to draw a regular pentagon, right? Regular pentagon. So that only 1/5 of a turn will get you rotational symmetry. You could really draw anything that had 5-fold rotational symmetry. Something like this. It could be a little squiggly star, right? And after 72 degrees or 1/5 of a turn, you'd have, again, your same squiggly star. C, an angle of rotational symmetry of 180 degrees with 2 lines of reflectional symmetry. We've actually seen this before. Take a look back at this one. You could do that exact thing right there. You could draw yourself a rectangle, give yourself 2 nice lines of reflectional symmetry and 180 degrees of rotational symmetry. Or, well, you could do a little better. You could go even farther back and take a look at something like this H, right? That H had 2 lines of reflectional symmetry. In fact, let me bring that H down here. Again, the H had 2 lines of reflectional symmetry. We talked about that before. But also, you could have rotated it 180 degrees and gotten the same H. Okay, so that would have worked too. Either of those shapes are fine, and please draw your own. As for this last one, which should be labeled D, my apologies, an angle of rotational symmetry of 180 degrees with no lines of reflectional symmetry. Oh, this is interesting. So it's got to look something like from C, something like these, but it can't have any sort of reflection. Well, think about something like this symbol right there, which actually is the symbol on the Isle of Man. That had rotational symmetry, but no reflectional symmetry. So what if I drew something like that, but with 180 degrees instead of 120? What if I drew a shape like this? Right there, kind of like this. It doesn't have any lines of reflection. If I try and draw one here, that's not going to work. That's not the same. If I try and draw on one here, again, that doesn't exist over there. Can't even do a diagonal one because then there would kind of be this shape over here. That's not going to work. So no lines of reflection, but if I were to rotate it, okay, I get, boom, back the same original shape. So that would work right there. That's a pretty good one. And I mean, you could get a little fancier if you wanted to, right? I could do something as fancy as this. Maybe add some of this, something like that. There's no lines of reflection here. Notice I can't really draw any sort of lines here. That's not a reflection line here. That doesn't work. Even a diagonal, no, nothing like that's going to work. But if I rotate it the right way, 180 degrees, I can get right back to where I was before. So hopefully this video has shown you the different kinds of transformations that map onto themselves, the reflections and rotations that don't change the figure at all, and that simply transform back on to themselves.